Hi there, my name is Christopher Wurst and welcome to the first video of the Homework 2 playlist for Material Energy Balance. This video will be going over question 1, as you can see on the screen here. So question 1 says, using a schematic PV diagram with isotherms below, at, and above the critical temperature, explain how the critical point can be used to determine the A and B parameters of the van der Waals equation of state, then derive expressions for these parameters in terms of critical properties, and then derive the critical compressibility predicted by the van der Waals equation of state and explain its relevance. So, I'm going to first pull up a pressure volume phase diagram, and you can see here it, instead of the usual, let's find a pressure temperature, instead of the usual pressure temperature phase diagram where it relates pressure and temperature, you find your liquid phase, your solid phase, your triple point, your critical point. Pressure volume diagram has solids over here, a mix of solid and liquid phases here in this middle part, a subcooled liquid and a superheated vapor, and then the mix between liquid and vapor in this hill. Now up here is the critical point, as well as isotherms, which is just lines of a specific heat here. Now you notice that this is horizontal, which means this is a general guess. There's no actual, you're not able to figure out the temperature in this area well. This line doesn't actually exist, it's just a connector. So, to explain the critical point can be used to determine the A and B parameters of the van der Waals equation of state. Let me pull up the van der Waals equation of state. Van der Waals equation. So, images. Here. Good. So, pressure equals, the van der Waals equation of state is the pressure equals the moles times R times the temperature divided by the volume minus the moles times B, and A and B are variables that are explained within the equation of state. Now and minus the moles squared times A divided by the volume squared. Now we're going to be using specific volume, which is equal to the volume divided by the number of moles. Now we're going to assume the number of moles is 1. So, and let me get up real quick. If we had the ideal gas law, pressure times volume equals moles times R times T. Well, if small v, specific volume, equals V over N, N equals 1. V equals specific volume equals big equals normal volume, and N cancels out. So the actual one that we're working with is PV, P little v, pressure times specific volume, equals R times the temperature. That means that the van der Waals equation that you see on your screen here actually cancels out to pressure equals RT, R times the temperature, over little v, specific volume, minus B, all minus. Moles cancels out, so it's just A over specific volume squared. So, and the critical compressibility, which we will need later, is an important factor here. It's called Z. So Z, critical compressibility, equals RT over PV, or PV over RT. Actually, no, it's it is just pressure times specific volume divided by RT, R times the temperature. So why does this matter in terms of the critical point? Well, if you can look up here at the isotherm, the critical point right here is a point of inflection, which means that not only is the first derivative 0, the second derivative is 0. We can use those, since we have two equations that equal 0 and equal each other, we can use that to find A and B. So, if we're using that here, then the first thing that we need to do, and then we can, when I get up, we can work that out. So, let's take the derivative. So we have P, actually, I already have it here. So, call it P prime, or the derivative of the van der Waals equation. Now, important thing is that this can only equal 0 at the critical point. So, this needs to be critical temperature, or sorry, temperature equals critical temperature, and volume equals critical volume. So, that means that if we take the derivative here, equals negative R times the temperature over V minus B, specific volume minus B squared, minus 2, it should be plus, because this is negative, so plus 2A over specific volume cubed. Now, important thing to note here is that temperature must be critical temperature, and the two specific volumes must be the two critical volumes. And this all equals 0. Now let's do it again because we have two unknowns. So we have pressure, the second derivative of the pressure at the critical temperature and the critical volume equals positive 3 times R times critical temperature over, not 3, 2. Here, minus critical volume minus B, divided by the critical volume minus B cubed now, minus, again, because this is negative power, 6A over critical volume to the fourth, and again, since this is an inflection point, this means that this is 0. So now I'm going to put all of these on either side, so R times critical temperature, and we're using, this top one's going to be the first derivative of the pressure, R times critical temperature divided by critical volume minus B squared equals 2A over critical volume cubed. And then here, moving this over, 2 times R times critical temperature divided by critical volume minus B cubed equals 6A over critical volume to the power of 4. So now, we're going to do inverse multiplication. So, we move to this side. I'll write it out here. R, that's bad on this. R times critical temperature times the denominator here, critical volume minus B cubed over critical volume minus B squared times 2 R, sorry, let me silence this. There we go, no more interruptions. Times 2 times R times the critical temperature. This cancels out entirely. These two cancel out. We're left with that. That goes down to critical volume minus B over 2 equals, and now we're going to inversely multiply these. Let's do, yes, 2A times V critical volume to the 4th power minus, divided by 6A times critical volume to the 3rd power. These cancel out, 4 cancels out, goes to 1/3 critical volume. These are equal to each other. Now, B is alone, we can get rid of it, or we can solve for it. So, if we have multiply by 2, so critical volume minus B equals 2/3 critical volume. We can add this, subtract this, so critical volume minus 2/3 critical volume equals B. B equals 1/3 the critical volume. Okay, we have that. Now we can substitute that back in to any of these. This one's easier. This one's easier. So we're going to do, you can also substitute it back into here. I'll substitute it back into here. We're gonna substitute back into the first derivative because it's equal to 0 and they're equal to each other. It works better. And remember, this is only, B is only at critical temperature, critical volume. This is only the case at the critical volume. Now, let's substitute back in, so R times critical temperature divided by, now, VC, critical volume, minus B, so critical volume minus 1/3 critical volume squared equals 2A over critical volume cubed. So, let's arrow down, R times critical volume divided by, this is now 2/3 critical volume, or 2/3 critical volume squared, 4/9 critical volume squared, so if, since this is divided by a complex fraction, this is 9/4 critical volume squared equals 2A critical volume cubed. Let's multiply this over, divide this, goes to A equals 9/8 R critical temperature, critical volume cubed over critical volume squared, cancel, so I'll erase this, equals R critical volume, critical temperature, critical volume. So now we have A. So, now we have A. So, let's put this back into here. I'm going to erase some of this work so I can free up some area, and I'll write these up top. So B equals 1/3 critical volume, A equals 9R times critical temperature, critical volume, over 8. We'll erase these. So, let's sum them back in. Now, negative. I've got a negative here. It's possible I might have forgotten a negative here. No, we didn't. We're good. So negative R times, you see, I'm going to keep that. So 2A over critical volume cubed equals R times critical temperature, critical volume minus B squared goes to, now we're going to sub in 2 9/8 R times critical temperature, critical volume times 1 over critical volume cubed. These cancel, this is a 4, equals R times critical volume, temperature over the critical volume minus 1/3 critical volume squared goes down to 9/4 R times critical temperature times critical volume. These actually cancel, this is 2 over 9/4 R times critical temperature R times critical temperature divided by critical volume squared. There, that's better. Equals, so R times R times critical temperature over 4/9 critical volume squared, and we'll pull this out. So this is total. That's just equal to each other, now that I think about this. You know what? I was right on the money on the first time. We actually do have to go back to the original equation. So, P equals, now, if we're using the critical point, critical pressure equals R critical temperature, critical volume minus B minus A over critical volume squared. There. This will get us to C, the critical volume, the critical compressibility. So let's sub in. We're going to sub in again. Critical pressure equals R times critical temperature over critical volume minus 1/3 critical volume minus 9R critical temperature, critical volume over 8V critical volume squared. Cancels out, goes to critical pressure equals R times critical temperature over 2/3, so 2/3 critical volume, which means this is actually 3/2. So 3/2, so 3 over 2 minus 9R critical temperature divided by 8 critical volume. Okay. So we can factor these out. Critical pressure equals R times critical temperature divided by critical volume, 3/2 minus 9/8. So we're going to multiply this over. Critical pressure times critical volume over R times critical temperature equals, well, 3/2 times minus 9/8 is 12/8 minus 9/8 equals 3/8. You know, this looks familiar. It's because it's compressibility. So, Z, again, critical compressibility equals 3/8. What does that mean? What's the significance? Why did this earn a Nobel Prize? Well, it's because this is saying that at any point for any compound, the critical compressibility of that compound is always 3/8. That means you can really sub it in for anywhere. You could find B and A easily. It really simplifies a lot of things in it. And from it, you can pull cubic equation states as well. So I'll be stopping the video there. We've already done all of this. That will answer question 1. Thank you very much for watching. Hope you have a good day.